The Shomprasad list is an expanded blind 75 with questions structured in a pattern form so that when you are solving arrays problem, then you solve other arrays problem to emphasize that knowledge that you just acquired. And if you are solving fast and slow pointers, the next question you solve also uses the same pattern and it helps you to reinforce the pattern that you learned. And also the difficulty goes from easy to medium to hard. And this is why I think that this is such a good way to practice data structures and algorithms and really become familiar with the patterns and how to solve the problem. There's also a playlist for retracking the problem. And so now we'll just continue with the next question on the list, which is majority element. So let's solve the majority element. We are told that we have an array of norms of size n and want to return the majority element. What qualifies as the majority element? Majority element is any element that appears more than half the size of the entire array. So we can see from the first example that we are given 3 to 3, and this means that the array is of the length 3. And so when we divide 3 by 2, when we floor it, right, we get 1. So a majority element must be greater than n over 2, than half the size. And so half the size is 1. So the majority element must be greater than 1. And we are told that we may assume that the majority element would always exist in the array. So we know that would always have an element that is greater than half of the total length of the array. Now, how do we solve this? Well, the brute force solution is pretty simple if we think about it intuitively. How can we keep track of the most occurring number? Because we can just assume that the most occurring number is going to be the majority element, right? So we can choose to loop over the values in this array and have a kind of like storage technique to keep track of the number of times that they occur. So when we loop through this array 3 to 3, we would have that 3 occurs once, then we would move over to the next item in the array and we'll say that okay, now we have 2 also occurs once, and then we move over to the final item in the array and we have 3 and we say that okay, 3 has occurred before, so let's increment the number of times that it's occurring, and then we see that 3 occurs 2 times and we just return the most occurring number, which is going to be the majority element, and that is 3. Now this works fine, but we've been given a constraint to solve this problem in linear time and constant space. Now this approach uses linear time obviously because we are looping through the entire item given in the array, but we use linear space, also use extra space, because we are keeping track of the number of items given or the items given and the number of times that they occur. That's going to use a set, a hash map. An object is a different data structure that we're using to store this, and that is a linear space. So in our follow-up, we are asked if we can do this in constant space, and this is not intuitive. It follows a book algorithm. The Boyer-Moore voting algorithm is a textbook algorithm that is designed specifically to keep track of a majority element in linear time and constant space, and that is what we are going to be using to tackle that constraint of linear time, constant space, but we're also going to be coding up the brute force approach since it is most intuitive. The more optimized approach uses the Boyer-Moore algorithm, which is an algorithm for finding the majority of a sequence of elements using linear time and constant space. Like I said, the algorithm was basically designed for a question such as this. And then there is also a pseudocode according to Wikipedia, which is what to be using directly in this code. And for every first, we are initializing an element m and a counter for each element x. That is when we are looping through the array. If the counter is 0, which it would be initially, right? Because when we initialize a counter, there is nothing that has counted, so it is 0. So if the counter is 0, then the element m is going to be equal to the element x. The element m is the variable we initialized at first, and the element x is the current variable that we are currently at. But if the counter is not 0, then we check is the element m equals to the element x. If it is, we increment the value in the counter. If it is not, we decrement the value in the counter. And at the end of the array, we just return the element m. Now, to conceptualize this better, obviously, let's look at how this might translate into code. So let's call our element m. We're going to initialize it to 0 because at first there is nothing there, and then we'll call our count. We're going to call our count 0 2. So the first thing we're going to do is we're looping through the array, right? We're looping through the entire array. So let's start at the very first item in the array, and now we check that, okay, is our count equals to 0? And it definitely is, because we've not done anything yet. So that means that our m, since our count is equals to 0, our m, which is the element basically, is going to be equals to 2. Now our count is going to be incremented to 1. Now we move on to the next item in the array, and we check again, right? What is our count? Is our count equals to 0? Our count is no longer equals to 0. Our count has now been incremented to 1. So what do? Now we move on to the next step. Since it has been incremented to 1, we want to increment. We now check that this, where we are currently are, is it the same thing as our m? And yes, it is. So what do? Increment our count to 2. We just add 1 to it, and now we move on to the next item in the array. We have 1. So we check our count is 2, is not 0. So we check that, okay, is 1 equals to our current majority elements, because basically this one is just saying, okay, this is the highest existing element. This is the element that has been existing the highest so far. So now when we now move over to the next item in the array, we now check, is it equals to what has been existing so far? And no, it is not equals to it. So what do? We are going to decrement our count by 1. We decrement our count by 1. Then we move on to the next item in our array. The next item in our array is 1. Recall that our highest occurring is still 2. So when we now check that, okay, are they still the same? We see that no, they are not the same. 1 is not equals to 2, but so we decrement our count once again to 0. And now that we have 0, we can now go ahead and replace 2 with 1. So 2 is no longer our highest occurring number. 1 is now our highest occurring number. So we go over to the next item, which is 1. Now we check that, okay, is 1 and 1 the same? Yes, 1 and 1 is the same. So what do? We increment our count back from 0 to 1. Right, now we go again to the next item in the array, and we now check, okay, is 2 equal to the highest occurring number in our count m? No, 2 is not equals to 1. So what do then? We now deduct. We don't yet replace. We don't replace until the count is down to 0. So what do? We instead take away 1 from our count to be 0. Now that we take away 1 from our count to be 0, we then move on to the last element in the array, and we see that we have 2. So is 2 equals to 1? No, 2 is not equals to 1. Now our count is 0. Once our count is 0, we have the right to replace the highest occurring with the number, which is now going to be 2. Now the logic behind this is that because there is a majority element, there is one element that is greater than half the number. So no matter how many numbers they are, there will always be one number standing. It's going to be like the survival of the fittest. Even if you have 1, 3, 3, as long as 2 is occurring more than half the size of the array, 2 will always be the last number standing. That's basically how the algorithm logic works. And you can play around with a number of test cases, because it is a bit difficult to wrap around like, why does this work? How does this even make any sense? But it begins to make sense when you understand the concept of 1 will always survive. If we have 3, 3, 3, 3, if we have 2, 2, 2, or if we have 2, 2, 2, 3, 2, 3, 2, 3, no matter how scattered they are, because we have these numbers occurring more times than this one will always survive last. It will always outlive the ones that exist less. And that is the whole logic behind the Boyer-Morse voting algorithm, that the number that occurs more than half the time, if you start cancelling them out to the number of occurrence, it would always exist. Now let's look at how this translates to code. So first, let's solve this question using our brute force approach. I'm going to define a variable called object. and it's just going to be assigned to a empty curly brace, because remember, we want to keep track. The first algorithm says we are just keeping track of the number of times this occurs, so we would have something like this basically. So this is what we want to do, and we also want to go ahead and define our result and maximum count. So our result is going to be the number that is occurring the highest, and our maximum count is going to be basically keeping track of the highest number of occurrences that we have had. Now let us loop over our array. So we're saying when I is equals to 0, then I is less than the length of the nums, then I plus plus. So what do you want to do now? I want to check that, okay, object of nums of I. So remember that I is just the index, so nums of I is going to be like so object 3. So the I that we currently are on is equal to 0. So the number at position 0 is 3. So we're saying that, okay, objects, the way we check objects is we call the object and then the property name. So basically this is going to loosely translate to object of 3. And what do we want to do with the object of 3? Or what will the object of 3 give us? The object of 3 is going to give us the value pair of the property 3. So we're going to check that the value of the property of 3, we're going to add 1 to it. So basically, let us say that we're already building out our object and we have 3 as a key. The value is 1. So what we are doing now is that we are getting the value of this key, object 3. We're getting its value and we're adding 1 to it to increment it. But in this instance, we've never encountered 3 before. So what do? If we've never encountered 3 before, we're telling our array basically to just either add 1 to what we currently have or assign it to 1. So for this first instance, 3 has no value yet. So instead of adding 1 to the value that does not exist yet, we are going to be having 1. And then when we move on to the array, because this is what we currently have in our array, and we are looping through. So when we move on to the next item in the array, we are going to have 2. 2 has also not been seen before, so we'll be assigned 1. Then finally, when we move on to the second item, which is the last item, index 2, we're going to see that is 3. So we're going to check, as 3 exists. If we say yes, 3 exists, what is its value? 1. So we just add 1 to it, and that is going to equal 2. So this is what this line of code is doing. Now that has been done, we just want to go ahead and check that does the value of the current nums, so the value of the current elements that we are at, is it greater than the max count? I recall that our max count is 0. It just represents that, okay, the maximum count that we have encountered, either of all the numbers in the array, is the value of it greater. If it is greater, then we want that our result is going to be the nums of I, is going to be the key. So basically, when we are looping through the array, we also want to check, now that we've looped through this number, let's say 3 is now assigned to the value 1. What's our maximum count so far? First, our maximum count is 0. So since our maximum count is 0 and we encounter that 3 has occurred once, definitely 3 is going to be like the largest. So when we move forward, we see that, okay, no, 2 is also the largest. We move on, we see that, no, 3 has occurred 2 times. So basically, that is what we are doing here. We want to check that the value of the object, if it has occurred the most, the one that has occurred the most, basically we want to keep track of that value. And then we also want to update our max count, so that our max count will always be the highest number of counts that we have seen so far. After all is said and done, our res is going to hold the value or the key that has the highest occurring value. We can just go ahead and return our res. Now this is going to work fine, but the only problem with this is that it uses extra memory. This object is going to be storing key value pair, and that is using extra memory. So now let's look at the Boyer-Moore's voting algorithm that uses linear time and constant space, and is much more simpler than you think. Alright, now so we've cleared our workspace and we want to dive into the second algorithm. According to the code, first we are defining the result, that is going to be the element m, and we're also defining our maximum count, the maximum number of counts that we have encountered. Initially, let us set both to 0, and we want to loop over the elements in the array. So we're looping over this and want to check that if count is equals to 0, which is going to be equals to 0 at first iteration because we've not done anything, then want to say that the result is equals to num. So basically we are saying that our highest occurring number at this point is equals to num because that is the highest we've seen so far. We're just assuming, right, that is the highest we've seen so far, like we had with our 2 2 1 1 1 2 2. When we start the iteration, our max count, and not count in this case, this is max count, our max count is equal to 0 initially because we assigned it to 0, and so we're assigning this rest to be the first item, which is 2. Now, but what if our max count is not 0? What do we do then when our max count is not 0? Now we said that we want to check that is this num that we are currently at, is it equal to what we call the highest that we've seen so far? If it is equal to the highest that we've seen so far, then we want to increment 1 to our max count. This is what we are doing here. So this is a ternary operator, right? Is num equal to the highest we've seen so far? If it is, we want to add 1 to our max count. Otherwise, we want to remove 1, and we remove 1 by just adding -1. So basically everything we did with the array thing, so we're moving, is it equals to 0? No, it's not equal to 0. Then rest is equals to num. Now that rest is no longer, now that our max count is not 0, what do we do then? We just check, is our current number equal to the maximum that we've stored so far? If it is, increment it by 1. If it is not, decrement it by 1. That is all we are doing here, and we just want to go ahead and return our result. Our result is going to be the highest occurring number so far. When they've all cancelled out each other, the one that occurs the most would somehow have its last card, like, hey, I still have one more child to play, I still have this joker card. That's basically the logic that it follows. Let's submit this and also see what we get. And as you can see, this also works fine. Now we are tracking the Sean Prasad list, and this is going to be part of the playlist. If you want to catch up with what we've done so far, I highly recommend this playlist. It is one way to really cement the patterns that you're learning in data structures and algorithm. And thank you so much for watching. I will see you in the next video.